Okay, so today we're going to review state machines, basically, because you guys are really close to knowing everything you need to know in order to complete the class. We really just want to start reinforcing some of the ideas. We'll still have a few more lectures. I'm really close to finishing the grading of the exams. I've actually finished the marking. I'm just assigning points and figuring it out. And then I'm going to come back, and there's a few things that are not clear to you guys, which I've come to understand based on the exams. And the interesting is, one is the things that you don't understand is very different than the things the night class doesn't understand. And it's a very large discrepancy between the two. So I have to figure out the right way to present the material that we're kind of missing so that we can kind of all get to the same page while not having a lecture that feels like it's very eclectic, just bouncing around. So we'll do that. I'm also planning on getting down into the lab for at least 3 days between now and the end of the semester, so we'll have more lab time because that's a big part of what we're doing, right? It's a very practical application. We really only have, in terms of this, I think like 1 or 2 more homework assignments that I'll post so that you can get some practice with the state machines. Probably 2, because there'll be one that's going to be how do you design them using K-maps, right? And then one of them will be kind of the VHDL side of the state machines. So it'll probably be 2 homeworks and then garage door lab, project 2, project 3. I know not all of you, some of you are done with project 2, some of you aren't. Hopefully you'll all get that turned in by, I think I'm going to change the due date to like Sunday night, and I'm just going to make it firm, because at that point, if you're not done, we just kind of need to finish it and move on, and we can provide you with someone else's project 2 to kind of build the controller around, because that's project 3 is we're going to build the controller for project 2. We're going to build the interface. But before we do that, we're going to do a garage door opener, because it's much easier to design a garage door opener because the only input is a button, right? You push a button and it starts going down. You push a button, it stops. That's what we're going to build. And then we'll build the state machine for the calculators, project 3. So let's talk about just state machines in general as the review. If you take my digital circuits course, we'll start off with basically K-maps and then state machines. So you'll get review there again, because it turns out they're really important. So we have 3 parts to any state machine. They're the next state decoder, the current state register, and the output decoder, right? Decoders being we look at some input and we translate to what should our output be, right? And so the next state decoder is combinational logic that looks at whatever the inputs are, and this could be a range of an input, right? So in the case of the garage door opener or a garage door in general, there's 2 inputs to your state machine, essentially, from the outside world perspective, which is the button that you push and the little sensor that you would walk over and it would not hit you in the head, right? That auto detect. There's really 2 inputs. And then there's the current state. Then the current state register, right, is just an array of D flip-flops. So it's clocked. This is the only portion of the state machine that is clocked. And its whole job is to look at this, which is the signal next state, and on the rising edge of the clock, it takes that and pulls it into current state, right? This is basic. State, because we have to know where we are to know where we go next, right? If this is a counter state machine, we can build a counter as a state machine. I have to know that I'm currently at the number 5, so I can tell my next state decoder to go to the number 6, right? You can do that. It'd be clunky, but you could. The other purpose of the current state is, what are my outputs during this state? Okay. However, the output decoder can be more complicated in that it could potentially also care about the inputs. Do you remember what the difference between the 2 types? Like, do we remember the names? Mealy and Moore. If I have this connection, is it Mealy or Moore? Mealy, because a Mealy, the outputs depend on both the current state and the input, That's the most important concept around this structure. And then we walked through a sequence detector where we built roughly the next state decoder and the output decoder. But what I'm going to do is I'm going to use just kind of an arbitrary state machine that we're going to go through how we would actually do that. Like how would we build the next state decoder and output decoder if we wanted to use the K-map method, right? Which we've done before, but it's been a couple of weeks now. So let's bring it back and start reviewing. Well, I'm first going to start by drawing a state machine, and it turns out I'm not even going to talk about what it does because you can just draw bubbles and build it. So it's going to take 4 states, 0, S1, S2, 2, S3. Oh, no, not that one. So that one goes out to there. This is 1, this is 0. This one is 1. This one is 1. That one is 1. This is 0. Where's the S2 0? There we go. 0. And then we go and check, right? There's a sanity check on this. If we want to make sure it's a complete diagram, we just have to check that we have all possibilities covered. I'm missing 1, right? I have the 1 exit here, but I don't have 0. So I need something that says if the input is 0, then we stay put. And then I think the only place on this one that is going to be true is here. So this is the in/out Mealy style transition notation, right? This is saying if I get a 1, the output is 1 and I go to state 0. The rest of these are dash zeros, meaning the output is 0 in any other case. This makes it really quite easy to deal with this type of output decoder, right? This output decoder, we could look at it, and if we didn't really care about complete minimization, we could just say if I'm in state 3 and I get a 1, then my output is 1. So it's just an AND gate that is state 3 and 1, right? So a 3 input AND gate, because how many bits do I need to represent all of my states? 2, because 2 to the 2 gives me 4 choices that are enough. You don't really have to have that memorized, because what we can do is we can just draw a truth table and start assigning states. Because what do we do next if I'm designing the circuit?
Draw a truth table.
Yeah, we really call this the state transition table or the state machine table, the SM table, either one, right? Because we want to know where am I and where do I go so that I can start assigning binary values to thing, which is what we know how to work with. And we do that by saying, this is my current state, right? The CS. And that's this signal coming out. That's how many bits I have. So keep that connection in mind. They're going to be S0, S1, S2, and S3, and we can assign them 00 state codes. Right? That's just saying that these states have binary numbers associated with them, because that's all computers know, right? Computers only know zeros and ones. They don't know S's. Then my next state is going to be what happens based on my input. So if I is 0 or I is 1. Now, I'll try and get an example before I do. So if you had 2 inputs, and I'm just going to do this, say that I have inputs I and A, then I would need to start labeling all of them. I would have IA, and this would be 0, 0, 0, 1, 1, 0, 1, 1.
That's how you do that.
And now I would have all possible. However, for now, we only have one input, so we don't have to worry about that. This is why many inputs start to get really difficult, right? It gets really hard to deal with 5, 6, 7, 8 inputs, which in the case of the calculator, we're going to have like 16, I think, inputs, which obviously we can't do, which is why VHDL is a useful tool. Reflections okay? You guys can see this? Anyways, we really have not I and I is all we have to worry about. And then we're going to have the output decoder, right? Which in the case of the output decoder, we might have the output called Z, right? What is Z doing basically? And this too, because it's a Mealy machine, depends on I as well. If it was more, it doesn't depend on the output, so there's no I in that column. It's just a single, there's not 2 columns, it's 1, because it's regardless of what my inputs are, if I'm in that state, this is what my output is. So that the mores are easy. I usually do the Mealy ones because they're more difficult, so they're a better example, but the more simplified the output decoder do really simple. Then we can either start labeling them as S0, S1, or we can skip to the codes. So this is a state name, this is the state code. If I look at the code, I just look at the state 0, and if I get a 0, in other words, not I, right? Because in the case of in out, it's I/Z. So my input is I, my output is Z. Then we would say, well, if I have not I stay in the same state. And if I do get I transition to state 1, which I've called state 0, 1. If I look at state 1, then if I get a 1, I go to state 2. So that's 1, 0. And if I get a 0, I go back to 0. If I get a 0 in state 2, I go back to 0. And if I get a 1, then I go to state 3. Then if I'm in state 3, and whether I get a 1 or a 0, doesn't matter, then I'm going to state 0. Then the only situation in which my output is 1 is if I'm in state 3 and I see a 1. So I come over here and I say I'm in state 3, I get a 1, this is a 1, everything else is 0. This doesn't have to be 0. On the exam, you notice how I gave you the state table. I had you 1, you drew the diagram. The next one, I gave you a transition and you do the table. And then potentially what I'll do is I'll give you a table and make you make the circuits. I very often do it like I did in this exam where I decouple the ones so you don't have these weird cascading errors that are a nightmare to grade, because I hate grading those. And so understand the flow, because you're going to have to do each of the steps on the final, but I will probably decouple at least at some point. It's not unreasonable to have to draw the diagram and then the table, and then I would probably decouple the circuit, because that part is just a nightmare for me to grade. So anyway, there will be some amount of decoupling, but there may be some linking. So make sure that you understand the flow, how to go from concept to design. Okay. On digital systems, the following course of this one, we'll start building way more complicated state machines than what we do in here to do real world stuff. The next bit is we need K-maps. And I don't actually need 4 bits, right? I don't need these 4 inputs. However, I just want to remind everyone that it doesn't really matter, because if I do and we can call it CS0, CS1 if we wanted, right? This is kind of Q, so I could also call it Q0, Q0, Q1, whatever I call it, as long as we're consistent that we know that we're talking about this signal. Because this signal that is 2 bits wide that's coming back into this next state decoder, that's what we're building, right? We're building combinational logic to go in here that looks at the 2 bits in the current state, the 1 bit of the input, and says, what's next, right? That's what we're building. That means, because I haven't assigned here, there's this implied don't cares down here. Right?
Can you just take off the bottom one that came out?
Yes, I can. I just want to remind you that that's really what K-maps are doing, is if I only have I only have 1 here, that's why we can draw this 3 variable K-map, is it really is a 4 variable K-map with just don't cares down here.
It's I and X.
Yeah, yes, exactly. So we can ignore that, or if we were to fill it out with the 1s and 0s, we'll end up with the same thing. Doesn't matter, because whatever variable is here will cancel out. No matter what we do, it'll cancel out as long as we get it right. Okay, so then we look at it and say, where do we pull the K-map values from? Well, I need to decide what I'm designing, right? The next state has to have 2 bits because the current state has 2 bits. So the states have 2 bits. So let's design the first bit of the next state output. So NS 0. Next state 0 being, this is my next state column of the table. It's these, right? So this says that when I'm in state 0 and I have not 0, it has a 0. That's this square. Now, this square is state 0, right? For 0, 0, 1. 0, 0, 1. Right, because this is I is 0, I is 1. This is 0, 0, 0, 1, 1, 1, 1, 0. Then I say, well, if I'm in state 1, which is just the next column over, then it's 0, 0. Next one, the 1, 0, 0, 1, but remember, we flipped the columns of the K-map because we need to maintain logic adjacency. And lastly, 0, 0. Then we go and write out the next NS1 K-map. We'll keep it simple here. One, and then we go over, and now we know the order, right? It's just pattern. As long as I label the locations the same, now I can just go 0, 0, 0, 1, 0, 1, 0, 0. Last one, the output decoder. The output decoder is easy because we have just a bunch of zeros, right? So we're going to do the same thing because this is a Mealy state machine. So this is the K-map for Z. Same situation, Q0, Q1. And then we just know if we're 1, 1, 1, which is easy to find, right? That's 1, 1, 1. Everything else is 0. We go to our K-maps and we recognize that we're wrapping around. Oh, this is blue. And this K-map just has 2 on its own. They're not adjacent. They can't simplify. This one has 1 on its own. Can't simplify. And now I can say things like my NS0 is equal to I and not Q0. Right, because the Q0 doesn't change as it wraps around. Remember K-maps a little? Okay, NS1 is I, and we could do it this way if we wanted. It doesn't really matter, right? Because in both cases, these are I's. So it's I and at not Q1, Q0, or this one, which is Q1. I just skipped the simplification of factoring out the I. And the reason I did that is because I could recognize, does anyone recognize what this is? It's XOR. Right, if it's 0, 0 or 1, 1, it's not true. This is an XOR. Which, if we're trying to build this out of universal gates, is not really beneficial, but if I'm writing this in VHDL, it's easier for me to write I and Q1 XOR Q0 than it is to write the rest of it, right? I just simplified my VHDL writing. The VHDL will then actually translate it into the universal gates for me when I synthesize it. So I simplified what's the easiest for me to type in VHDL. VHDL will turn it into the best circuit for me. Then it's just a matter of saying Z is equal to all ones. So I, Q0, Q1, done. We can then go back and look at this and kind of evaluate what this is. I literally just pulled a random one off the internet, had about the right number of states and transitions as I wanted. But basically it's saying that if it sees the sequence 1, 1, 1, 1, the output is 1. It's looking for the sequence 1, 1, 1, 1. It does not, however, detect, well, maybe it does. Well, anyways, we'll get into that later. But that's all it's looking for, is looking for 4 ones in a row. Now, we could make up applications like this. In fact, we kind of do something like this in some biological applications, because it turns out your body doesn't like to have standing voltages in it. So if we build prosthetics, for example, we install it in the body, we don't like long streams of ones because it starts building up too much potential that can damage the circuit. So we design circuits that are intentionally flipping zeros and ones, even if they're supposed to be a long string of ones. So because the body cares about the average of the voltage over time, so we build it such that it will not, it'll have an average of 0 basically. So anyways, this is what we're doing, is we're looking for long strings of ones, basically is what we're looking for. You will notice that if I wanted to detect more than that, because if I end up 4 in a row, if I get a 5th, I'm starting a new detection. So it's not detecting overlap. Right. Yeah. So if I wanted to detect overlap, I would have to redesign the state machine. And that would actually be a fair question to ask you on a homework is, here's a state machine that detects a long sequence of ones, fix it so that it keeps detecting for as long as they're still 1. Right? I could do that. So that's all there is to designing state machines as far as the breadboard is concerned. So now I'm going to switch over and we're going to start talking about the VHDL of state machines, because it turns out, as I said, 2 inputs is fine. But as soon as we have, say, 5 states, now I need 3 bits, and then I have, say, 2 inputs, then you would have to be able to do a 5 variable K-map, which I haven't taught this semester, so you're out of luck, right? So we have to go back and start thinking about it in terms of VHDL. How do we simplify this so that we can actually design complex state machines without having to learn more advanced kind of digital logic concepts? And in many ways, VHDL is what allows us to teach this course as a essentially freshman level course instead of making it a junior level course as mine is. Come on. Thank you. Okay, so let's drag some VHDL over and switch my zoom. Okay, so let's pull up this sequence detector. I'm going to record this so that you guys can go back and reference it. Unfortunately, the downstairs lab is being used right now. And in general, I think it's better to have you guys follow along with the code, but I think there is also some disadvantage to that because you kind of get caught up in trying to keep up with my typing rather than just paying attention. So I think having this kind of both ways that we've done it in lab and now out of lab, I think is going to benefit you. So we'll go ahead and progress through and talk about a little bit of what I've built before, right? So here's the sequence detector, and you'll notice that in this sources panel that you can kind of look, I'm going to go run and turn off the light so you guys can see better actually. Sorry, I don't have a good way of making this text bigger, but what we have here is called SecDet sequence detector, and underneath it I have three components. I have my output decoder, my next state decoder, and my current state register, right? I've explicitly built the three parts. The current state register, if I go and open that up and look at this, notice that this is just a process on clock and reset, and if I reset, current state goes to 0. Otherwise, if there's a rising edge of clock, current state is next state. There we go. It's a D flip-flop, right? It's 2 D flip-flops in parallel. I just built it. There we go. One thing I want to say so I don't forget, if you ever run your simulation and it gets stuck at saying 0 FS, 0 femtoseconds, 90% of the time for you guys, the reason is because you forgot items in the sensitivity list. You've left a blank sensitivity list. This is allowed in the test bench and only the test bench. However, in hardware, it needs to know what's getting plugged into my clock port, basically. What am I looking for as an enable signal to say, let's run? Because that's what VHDL is doing, is in the sensitivity list, if either one of these changes, anything in the sensitivity list changes, it runs through the process. In this case, it asks the question, is reset true? If it is true, it executes this if and ignores the else if. It's done, right? It's not if this and also if this. This is if this otherwise do this, right? Keep that in mind. And then we can go look at the next state decoder, and let's redesign it real quick. I gave you a quick example, but let's build this for the state machine that we just talked about, right? So I literally just go look and I say, well, my NS0 is input and not Q0. Well, here I use the inputs, I think CS rather than Q. Yep, I did. So NS0 then I say is S because I use S for sequence rather than I, and not QCS at location 0. And then for the NS1, I'm just going to bring that in and I'm going to say S and parentheses. Is it not? No, it's just Q, so CS at 0, XOR CS at 1. There we go. We just built our next state decoder. Then I can go open the output decoder. It also takes S and CS. And in this case, it is, wow, very slanty writing apparently. S and CS, basically. So S and CS at 0 and CS at 1. If they are all true, it's true. Then we go back up and look at the sequence detector where I have brought in the component next state decoder, current state register, output decoder, and I've wired them together as per the diagram. Now what I can do is I bounce over to the test bench. I have declared the component sequence detector, right? I only have to worry about that top level because once I have it, it automatically brings in these tier, right? This is my test bench. This is the sequence detector. These are the 3 components that make up the sequence detector. I've created the signals that plug into it. And then the test bench is quite easy. It's here I've gone ahead and reset and then stopped resetting. I'm generating a clock by saying clock, not clock TB after 5 nanoseconds. So every 5 nanoseconds, it's going to toggle back and forth. This only works if I have this line in there where I've told that clock I reset are all starting at 0, right? This colon equals is the initial value declaration saying this is where I'm going to start, starting at 0. Then, because it's a sequence detector, I'm literally just saying I is 0, I is 1, I is 1, I is 1, I is 0. And I just set the sequence, wait, set the sequence, wait, set the sequence, wait, right? So that it has a chance to clock in each one of those new I's. This is a different sequence. So let's come down here and I'm going to change it just a little bit. I start with hitting the zoom fit button. And then we can start looking at, is it doing what we think it should? So here, So if you click on one of the waveforms, I can now use the arrow to skip along to each place it transitions. So it's kind of easy if you want to just step through. So anyways, we've stopped resetting here. So I've clocked in a 0. And if I really want to see what's happening, what we want to do is come into this, the unit under test, and we can pull out the signals, current state and next state. And we always want those signals when looking at state machine debugging, because you will have no clue what's happening if you don't have that. It just doesn't work out very well. So what we see is we have a 0, so we're still in 0. We have a 0, so we're still in 0. But it has this brief moment where the next state thinks it's 1, right? Because the input has gone to updates the next state is to 1, because the next state decoder updates instantly. And then when that clock happens, it brings that little blip of a next state into my next state. And as soon as I enter my next state as 1, it goes, oh, look, my next state is now 2, because it updates as soon as I transition, which happened at that rising edge of a clock. There is a thing that you can do that can help you debug sometimes, which is inside of my current state register. Let's get it in the next state decoder. Is if I want, I can simulate what happens to the real system by doing this. Oh, that's funny. There we go. I think I have an issue because I've used the signal NS and I'm trying to use nanoseconds. So there we go. There we go. So now I've artificially introduced a 1 nanosecond delay. And so if I go and I rerun my simulation, now what we can do is if I go look at what's actually happening now, is you'll notice that the input changes and then 1 nanosecond later, my next state changes. Because I've now introduced a 1 nanosecond gate delay. And that can help you, especially identifying, because if you have signals like in project 2, especially that kind of feed back around on each other, if they all change at the same time, it can be hard to see which one causes the issue, because like they may go all dual driven and you may not be sure which one is doing it. Whereas if you introduce these delays, sometimes it's obvious that, oh, this signal is going dual driven first, therefore that's likely the cause of my issue. Now, something to keep in mind, this does not turn into hardware because hardware doesn't know what time is. So the after 5 nanoseconds is strictly for simulation purposes. It does not turn into hardware. Okay. Now, this is fine and dandy. We have a working state machine, I believe, right? Because we see a 1, 1, 1, and then our output is true. That's only 3 ones. Is that right? So we go 1, 1, 1, and as long as my output is true, as soon as I'm in here, my next state is going to update to this one. And so my output is going to be true because I'm in state 3 and I have a 1 there. So that's why the output goes true. However, then I clock it in and I go. So this state machine is a little bit odd in its behavior, I guess, in that kind of edge case. State 1. That takes us to state 2. That takes us to state 3. And then because our next state at that point is 3, goes to 3, and then we go back to 0. Yep. But as soon as the input stops being 1, the output stops being true. So I'm in state 3, but it dropped to 0. So we clocked in this 1 and went to state 3. It's looking at input is 1, we're in state 3, output is 1. We're still in state 3, the output changes to 0 in the middle of state 3. So the output drops, and we're still going back to state 0 because of the state machine. Whether I get a 0 or a 1 on that clock, I go to state 0.
So your output decoder is not
Correct. Yeah, because we built it as combination logic. We could clock it if we wanted, but this is kind of the behavior of Mealy state machines. This is kind of why Mealy state machines are hard to design, if I'm honest, is because of this type of behavior, because your outputs aren't necessarily true just because you're in a particular state. It's also looking at the inputs, and the inputs can change at any point during that state, which will change your output. So there's a particular difficulty around that because your output is not even true for a full clock cycle in this case. So the more state machines can be a little bit easier to build. And so let's go ahead and build a more state machine. But let's do it for something kind of a different one. Let's just go ahead and say, without doing all of this work, let's detect the sequence 110. Right, let's just change what we look for. And all we have to do that is think about what that means. So in the case of a more state machine, if I want to detect 3 numbers, I need 4 states. More state machines tend to take more states, just because I have a state dedicated strictly to letting me know what the output is true, right? And so I simply say we need 1, 1, 0, and this state is where Z is detected. It's true inside of that last state. Everything else, well, if I get a 1, 1, 1, I stay put, right? This state says I have a long sequence of 1s. I'll give them names as 0, S1, S2, S3. And then I say something along the lines of, well, if I get a 0 here, I stay put. If I get a 0 here, I go back. 0, I'm covered. 1, I'm stayed. Here, if I go 1, 1, 0, 0, I'm back. And if I go 1, 1, 0, 1, well, that's saying that I detected the 0 and then 1, 1. This state is that I've seen 1, 1. We come back to state 1.
S1 is the state where you've seen 1, 1.
Yes. Yeah, because state 0 is I haven't seen any ones yet. I see 1, 1, I come to state 1.
Yeah.
State 2 is I've seen at least 2 ones.
So what? Why did it go to state 2?
So 1,
Yeah.
a second 1, a third 1 stays put. So this is any number of ones greater than 1. I've seen 1, 1, or I've seen a 0. I've seen 1, 1. I've seen 2 or more ones. I've seen a string of 1s and then a 0. So I'm going to make a new file. So the first thing that I'm going to do is I'm actually going to use the exact same ports so that I don't have to change my test bench at all. And then we have to introduce a bit of a new idea, which is how we're going to address the problem of what happens if we have a million states, and I don't want to sit and assign state codes to all of them. We also want something like constants, right? Because there are better ways to call a state than 0, 0, 0, 1. We can kind of tell what they are, basically. We can use this new concept called types. I can make a new type, and I'm going to call it state type. The name is arbitrary, but it's descriptive in this case. State type. And I'm sorry, I'm going to forget the exact sequence. But then this is when I do this type, we're looking for an enumerated type, which is I'm just going to list all possible options that this state type can be. So I actually think it is. We'll find out. Sorry, if I screw my syntax, I'm sorry. I usually just copy and paste this, so I'm perfectly honest. S0, S1, S2, S3. And then I need a signal that is based on these types, right? I've made a new type. And a type is something like standard logic vector or signed or integer. These are all types we're familiar with. We've just made a new type. The problem with this type is it doesn't have any operations that go with it, right? It doesn't have logical operators necessarily. It doesn't have addition. It's just an enumerated type. If we want to do any manipulations on it, we'd have to write them. But we're going to have a current state and next state that are of type state type. And then inside of here, we are, of course, going to need a process, right? Because there's going to be a clock. And this process, its whole job is going to be model the current state register. That's the first thing that I'm going to build. So the current state register basically says if reset is 1, then next state is 0. Sorry, not 0, S0. Else if rising edge of the clock, then next state, oh wait, current state. We're building the current state register. Current state goes that. Otherwise, current state goes to next state. Right? That's just a description of what the current state register is doing. It's using the state type, so it knows what it's doing. Then I build a second process down here that is responsible for handling the next state register, or sorry, yeah, the next state decoder, basically. And it's combinational logic, right? And so we can build a process that is combinational logic simply by putting all of the inputs into the sensitivity list. Because if any change in any input will cause a change in the output, That's describing what combination logic is, right? So since it's sensitivity, let's tell it when to trigger. And I've let all of the inputs, therefore combinational logic. So here, I'm going to process on the things that I want to know if they change. So what I'm looking for, did my current state change, basically, right? So current state or S. Now here, we're going to introduce a new tool for you guys, which is really the fundamental building block of all of our state machines from here on out, which is the case statement. You might know it as a switch statement, depending on other program familiarities. But the cases are simply saying it's a when else that goes inside of a process. It's the same thing, we just have a different format for it, whether we're in a process or outside of a process. But we're just saying, based on where I am, right? Case on current state when, and now I just say, what is my current state? When S0, then I do stuff. I'm going to need an end case down here. Sorry, there's a when case then. I'll have to look that up. I can't remember the end. What am I missing? I think it is. Oh, come back. Can't see. There we go. KCS is. There we go. When S0. Now I just say what happens when I'm in S0. Well, what is S0 doing? It's making a decision, right? So during K0, if S, which is my input, equals 1, then next state is S1. Else, next state is S0. And if. When S1. We use this kind of the port mapping arrow in this case. Sorry, we have to keep track of the directions all of our arrows point, right? We have the signal assignment 1 and the port mapping 1 and this one, and they all kind of point different directions, which is annoying. But at this point, it's essentially for this particular kind of case state machine, just really copy and paste. It's just, where am I going? Well, if I'm in state 1 and I get a 1, I go to state 2. Otherwise, I go back to state 0.
Should you have if S or when S0 at the beginning, like on the first one? Not just if S.
No, it's when state 0, if S sorry, this is kind of weird, confusing name. So we have S, which is the sequence input, and S0, which is the state 0. Sorry, those were a little bit confusing, my bad. So now if I'm in state 2, if I get a 1, then I stay put. If I get a 0, then I go to state 3. For formatting, I strongly recommend putting a return after whatever the end of the previous state is to make it obvious where your states are. Do the tabs kind of like I'm doing here. Then I just update when I'm in state 3. If I get a 1, I go back to state 1. If I get a 0, I go back to S0. Done. Now the only thing left is my next state decoder, right? Or my output decoder, because this was my next state decoder. It's decoding all of my next states for me. So then all I have to do for that is a when else statement. It's just a conditional, basically. It's just looking at what my current state is. So basically I can say, what is my output called again? ZO. ZO gets assigned to 1 when current state is S3 and S, the input, is 1. Otherwise, else. All right, what's not happy here? Oh, ZO, not Z0. There you go. I built my output decoder. Yeah.
Is this the same way you would set up for like lab we're gonna have today?
Yes, this is exactly what you'll do for the lab today. However, I'm going to show you an even easier version. So what this has done is we've built 3 different blocks just inside of one file, which is simpler by far than trying to figure out the next state table and the K-maps and on and on and on. I just use conditions, right? If this is my situation, then go here, otherwise go here, right? It very simplifies it. But it turns out we can simplify it even further and I'm going to create a new source. Actually, I'm not going to create a new source. I'm going to go through and show you the changes. So here, we're dealing with updating the current state, right? That's all this process is doing. But it turns out I can start combining blocks and simplifying my life a little bit. So let's go down here to my output decoder. And I actually like this. I really like doing my outputs like this. In fact, for the garage door, this is the best way to do it. But let's say that I don't want to even build my output decoder because say my output decoder logic is complicated, right? This was easy output decoder. Let's say it's hard. Well, then all I have to do is come into this and say, well, when I'm in S0, Z naught is going to be 0, right? No matter what, inside of state 0, my output's never true. Inside of state 1, my output's never true. Inside of state 2, my output is never true. Inside of state 3, if I'm in state 3 and I see a 0, my output is true. Otherwise, false. Ta-da. Another cool trick, if you have a bunch of cases and say, let's say I have like if, else if, else if, else if, like 12 of them, which could happen in a state machine. And this is the case where Z0 is 1 and all the other ones are 0, then I can actually do this. Because this is a sequential statement. So what will happen is I'll come into state 3, Z0 is 0, and then it'll change to 1 because it goes in order. However, there's a trick with this one that could be problematic because currently if my input changes, it will change, it'll run this process again and it will change the output. So this will behave exactly the same way as the previous one, meaning that just because I'm in the state doesn't mean that my output will be the same. It'll change with the input. So I can actually combine the output decoder with my next state logic. I just did it, we're done. But guess what? I can keep combining. I can now bring in the current state register and combine it with this block too. And I do that by coming up to the top and literally just deleting the whole update process, updating this to just and reset. And now I'm just going to embed the case statement. If reset is 1, then CS is S0. Else if rising edge of the clock, then come down to the end of case. And if and now this case runs on the rising edge of the clock. So the only time my states are going to change is if I'm sorry, if the clock changes, right? So even my outputs are now clocked because they're inside of this process. There's one remaining error is I was initially going to do this. So I'm going to call this next state. And we're not even going to use current state. Current state's gone, which is a little bit confusing, but I'm going to explain why I've chosen next state. So when I'm in here, S0 is my current state, right? I'm saying case on next state, but I'm casing on where I am. So S0 is technically my current state, not my next state. However, on the waveform, it looks like next state. Because what happens is as soon as I enter S0, it evaluates this and updates the state. So I will be in state 0, but the signal NS will be S1 because it updates. So in the VHDL, it looks like current state. In the waveform, it looks like next state. So I've chosen next state so that when we view it on the waveform, it won't be confusing because we don't want to think that we're in state 0 when we're actually in like state 3, because it is looking ahead as far as the waveform is concerned. Because of the way I've written my sequence detector, I can literally just update my component from sequence detector to sequence detector 2 and update it here. All the ports are the same.
Just set it as the top level.
No, because my test bench is the top level. Test benches don't really care what the top level of the design file is. The top level of the design file only matters for telling the FPGA what the top level is. So once you get a synthesis. So by the way, if you start running synthesis on an FPGA and it ever pops up with a message and it's like your ports are not compatible and it lists ports that aren't part of your top level module, it's because you've selected something else as a top level module other than what you expected. That's a problem that we see a lot. So I don't have the output defined in the reset state. I may want to go back and reset that so the output is known, defined. But other than that, we can see it march through the things and make a detection. This detection, if you look at it, unlike the previous one, lasts a whole clock period from one rising edge to the next, because now we're a more state machine. It's a clocked output. Okay. So that's really 3 different ways that you can build state machines, and they are all correct. Well, 4 almost, right? It's use the K-maps, which is awful if we're all honest, right? No one would design a real system this way, but we need to understand it. We need to understand what's happening. The next way is to build each of the blocks separately with those processes, right? And then combinational like I did. In the case of the next state decoder, it's easiest to build it with a case statement inside of a process, which we make combinational by listing all of the inputs on the sensitivity list. And then finally, we can build the state machine all in one, right? We can pull them inside, building the process so that it looks like sorry, sequence detector 2 here, where the key components are. And if I'm honest, I would say that I build 90% of the state machines that I build as this style with the outputs combined inside of the states, because it's very easy to think about having states with specific outputs rather than worrying about the timing of a melee type machine's outputs. Now, I say 90% because sometimes you really do want the output to update as quickly as it can rather than waiting for the next clock. There are situations where that applies. not as many as more state machines in my experience. So main key factors of this one: process on clock and reset. If reset, do the reset condition. We probably want to set all the outputs here. So I should do Z, for example, as well. Reset the next state, then do else if rising edge of a clock, case on next state, and then these whens. This is saying when next state is S0. That's what this is saying. When the case of next state is S0, then we're going to make these assignments. When I'm in this state, these are the decisions I'm going to make. They're just if statements. We don't have to understand anything more than the logical flow. Okay. And so in the case of the garage door opener, this is going to look like, so one of the states is ready to go down, right? We're going to be sitting at the top. We want to be ready to go down. I'm going to push the button. It's going to start going down. So my case statement is when ready to go down, if button is 1, then move to state going down. If I am in state going down and the sensor is tripped, then go to state going up. Right? Most of the time they start going back up if you trigger the sensor, right? It's literally as simple as, what do I do in the state based on my inputs? If this, then that. If this, then that. This makes designing state machines of tremendous complexity very simple, as long as we can think logically. And this is really the foundation for a huge percentage of what you will do in digital systems. The rest of it turns out to be like signal processing and communication theory, but we'll get to that in digital systems a little bit. As for now, we're going to build the garage door this afternoon in our lab. We're also going to then move on to project 3 in the coming weeks, where we're going to build the state machine using this exact method for our calculator. And the calculator state machine is, oh shoot, I don't have the overhead camera on. Let me see if I can. Nope, I'm out of time anyways, it's fine. So we'll talk about project 3 in the coming days so that we can see how we start thinking about complicated systems and how they make decisions based on user inputs. Because this is going to be a state machine with at least a dozen states, I believe, is where we're going to be at. But none of them are harder to build than this. They just have more outputs that we have to list. Thank you.
Moxcon's still in lab right now.
Sorry, one second, let me